The relational model is one of the most popular data models in use nowadays. It was first formalized by Edgar F. Codd in his seminal paper, A Relational Model of Data for Large Shared Data Banks, which appeared in the well-respected journal Communications of the ACM already in 1970. The relational model is a formal model with a sound mathematical foundation based on set theory and first-order predicate logic. It has no graphical representation, which makes it less suitable to be used as a conceptual model. It consists of the following basic concepts. The database is represented as a collection of relations. A relation is defined as a collection of tuples that each represent a similar real-world entity, such as a product, supplier, employee, etc. A tuple is an ordered list of attribute values that each describe an aspect of this entity, such as supplier number, supplier name, supplier address, etc. Each tuple is uniquely identified by its primary key. Tuples are interrelated by means of foreign keys. Various commercial implementations exist provided by Oracle, IBM, Microsoft, etc. Let's provide some more detail. A relation can also be interpreted as a table of values. Here you can see a relation supplier represented as a table of values. A relation corresponds to an entity type in the EER model. Each tuple corresponds to a row in the table or to an entity in the EER model. Attribute types can be seen as the column names. These are identical to the attribute types in the EER model. Examples here are supplier number, supplier name, supplier address, supplier city, and supplier status. Each attribute value corresponds to a single cell. Table names and column names are used to help in interpreting the meaning of the values in each row. Let's now provide some formal definitions. A relation scheme R, denoted by R, A1, A2, A3, up to AN, is made up of a relation named R and a list of attribute types A1, A2, A3, up to AN. Each attribute type, AI, is the name of a role played by some domain, DI, in the relation scheme R. DI is called the domain of AI and is denoted by DOM AI. A domain specifies the range of admissible values for the attribute type. A gender domain can specify the values male and female. A time domain can specify time as day, followed by month, followed by year. R is the name of the relation scheme. It is recommended to use a meaningful name to facilitate its understanding. Here you can see some examples. A relation student with attribute types student number, name, home phone, and address. A relation professor with attribute types social security number, name, home phone, office phone, and email. A relation course with attribute types course number and course name. A domain can be used multiple times in a definition of a relation scheme. Assume we define a domain prod number representing integer values between 1 and 9,999. Let's say that we want to build a relation bill of material representing which product is made up of which other product in what quantity. Think of a bike consisting of 2 wheels, a wheel in turn consisting of 30 spikes, etc. This can be represented as a relation bill of material with major product number, representing the composite object, minor product number, representing the part object and the quantity. The prod number domain can now be used to define the attribute types major product number and minor product number. An advantage of using a domain here is that if the product number definition would ever have to change, such as between 1 and 99,999, then this change should only be done in the domain definition, which seriously improves the maintainability of our relational model. A relation, also called extension R for the relation scheme R, A1, A2, A3 up to AN, is then a set of M tuples, R equals T1, T2, T3, Tm, whereby each tuple T is an ordered list of n values, T equals V1, V2, V3, Vn, corresponding to a particular entity such as a particular supplier, student, etc. Each value Vi is an element of the corresponding domain DOM-AI or is a special null value. A null value means that the value is missing, irrelevant, or not applicable. You can see some example tuples listed for the student, professor, and course relations. More formally, a relation R is a mathematical relation of degree n on the domains DOM-A1, DOM-A2, DOM-A3 up to DOM-AN, and is a subset of the Cartesian product of the domains that define R. Remember, the Cartesian product specifies all possible combinations of values from the underlying domains. Of all these possible combinations, the current relation state represents only the valid tuples that represent a particular state of the real world. You can see this illustrated here. We have three domains: prod idea, defined as an integer between 1 and 9,999, product color defined as either blue, red, or black, and product category defined as either A, B, or C. The Cartesian product of these three domains then simply lists all possible combinations. Our relation R will then be a subset of all these combinations. It is important to note that the relation essentially represents a set. Hence, there is no logical ordering of tuples in a relation. A relation also does not have any duplicate tuples. There is, however, an ordering to the values within a tuple based upon how the relation was defined. According to the relational model, each attribute type is single-valued and atomic. Hence, no composite or multi-valued attribute types are allowed. As we already mentioned, a null value corresponds to inapplicable, irrelevant, or unknown. The relational model allows to define various constraints on the values of the attribute types. In what follows, we will discuss domain constraints, key constraints or uniqueness constraints, entity integrity and not null constraints, referential integrity constraints, and semantic integrity constraints. The domain constraint states that the value of each attribute type A must be an atomic and single value from the domain DOM-A. Suppose we have a relation course with attribute types course number, course name, and study points. The first tuple is a correct tuple specifying course number 10, Principles of Database Management, with 6 study points. The second tuple is incorrect, as it specifies 2 values for the course name, Principles of Database Management and Database Modeling. To understand the key and uniqueness constraint, we first need to discuss the concept of a key. As we already mentioned, a relation is a set of tuples. Hence, all tuples in a relation must be distinct. No two tuples can have the same combination of values for all their attribute types. A superkey is defined as a subset of attribute types of a relation scheme R with the property that no two tuples in any relation state should have the same combination of values for these attribute types. In other words, a superkey specifies a uniqueness constraint, in the sense that no distinct tuples in a state can have the same value for the superkey. Every relation has at least one default superkey, the set of all its attribute types. A superkey can have redundant attribute types. As an example, for the relation student, student number, student name, and student birth date is a superkey, but note that both student name and student birth date are redundant, and student number is a superkey as such. A key K of a relation scheme R is a superkey of R with the additional property that removing any attribute type from K leaves the set of attribute types that is no superkey of R. Hence, a key does not have any redundant attribute types and is also called a minimal superkey. For a student relation, student number is a key. In general, a relation scheme may have more than one key. As an example, a product relation may have both a unique product number and a unique product name. Each of these keys is called a candidate key. One of them is designated as the primary key of the relation. In our product example, we can make product number the primary key. The primary key will be used to identify tuples in the relation and to establish connections to other relations, as we will discuss in what follows. It can also be used for storage purposes and define indexes in the physical scheme. The other candidate keys are then referred to as alternative keys. In our example, product name can be defined as an alternative key. The attribute types that make up the primary key should always satisfy a not null constraint. Otherwise, it would not be possible to identify some tuples. This is called the entity integrity constraint. A not null constraint can also be specified for the other attribute types, such as the alternative keys. A relational database scheme S is a set of relation schemes R1, R2, R3, Rm, and a set of corresponding integrity constraints IC. A relational database state dB of S is a set of relation states R1, R2, R3, Rm, such that each Ri is a state of Ri, and such that the relation states satisfy the integrity constraints specified in IC. The DBMS will have to take care that the integrity constraints are always checked and violations reported if the database state is updated. Here you can see an example of a relational database scheme for a purchase order administration. It includes 5 relations: supplier, product, supplies, purchase order, and PO line. Each relation has a set of corresponding attribute types. Here you can see an example of a relational database state. Note that each tuple has atomic and single values for each of its attribute types. Similar to relationship types in the EER model, Also, relations in the relational model can be connected. These connections are established through the concept of a foreign key. A set of attribute types Fk in a relation scheme R1 is a foreign key of R1 if two conditions are satisfied. First, the attribute types in Fk have the same domains as the primary key attribute types Pk of a relation R2. Next, a value Fk in a tuple T1 of the current state R1 either occurs as a value of Pk for some tuple T2 in the current state R2 or is null. These conditions for a foreign key specify a referential integrity constraint between two relation schemes R1 and R2. Let's illustrate this with an example. To the left, you can see our ER relationship type on order, which says a supplier can have minimum 0, maximum n purchase orders, whereas a purchase order is always connected to minimum 1, maximum 1, or in other words, exactly one supplier. How can we now map this ER relationship type to the relational model? The first option would be to add purchase order number as a foreign key to the supplier table. However, since a supplier can have multiple purchase orders, this would create a multi-valued attribute type, which is not allowed in the relational model. A better option is to include supplier number as a foreign key in the purchase order table, since every purchase order is connected to exactly one supplier. Since the minimum cardinality is 1, this foreign key should be declared as not null. In our example, you can see that purchase order 1511 is supplied by supplier number 37, whose name is ad fundum, and purchase order 1512 is supplied by supplier number 94, which is the wine crate. Here's another example. We have an end-to-end relationship type between supplier and product. In other words, a supplier can supply 0 to n products, whereas a product can be supplied by 0 to m suppliers. How can we map this end-to-m relationship type to the relational model? Well, let's explore our options. We can add a foreign key prod number to the supplier table. However, since the supplier can supply multiple products, this would create a multi-valued attribute type, which is not allowed. Vice versa, we can also add supplier number as a foreign key to the product relation. Unfortunately, the same problem arises since a product can be supplied by multiple suppliers. The solution is to create a new relation supplies where we include two foreign keys, supplier number and product number, which together make up the primary key of the relation. We also add the attribute type of the ER relationship type to this relation, purchase price and delivery period. You can see that this relation perfectly models the end-to-m cardinalities. Supplier number 21 can supply products number 289, 327, and 347. Vice versa, product number 347 can be supplied by supplier numbers 21, 69, and 84. Here you can now see the relational database scheme for a purchase order administration. Primary keys are underlined and foreign keys have been put in italics. Just as with the other data models we discussed before, also the relational model has its shortcomings. More specifically, there are some more general constraints that cannot be enforced in the standard relational model. Examples are: a supplier can only have purchase orders for products he or she can supply. A student should not take more than 6 courses per semester. An employee should always work in a department he or she manages. Employees should work on projects assigned to departments to which they belong. As we will discuss later, extensions have been developed to the relational model to enforce some of these constraints using, for example, stored procedures or triggers. Here you can see an example relational database scheme and state for a purchase order administration. As you can see, there are no inconsistencies or duplicate information. This is why we call this a normalized relational scheme. Here you can see another example of a relational database scheme and state where we have only two relations with all the information. You can see that the suppliers relation now also includes all the attribute types for suppliers, such as supplier name, supplier address, etc., and all the attribute types for product, such as product number, product type, etc. You can also see that the PO line relation now includes purchase order date and supplier number. It is clear to see that this relation scheme contains a lot of duplicate information, which may easily lead to inconsistencies. As an example, in the supplies table, all supplier and product information is repeated for each tuple, which creates a lot of redundant information. This is why we call this an unnormalized relational scheme. At least three types of anomalies may arise here: an insertion anomaly, a deletion anomaly, and an update anomaly. Suppose that we wish to insert a new tuple in a supplies relation. We must then be sure to each time include the correct supplier and product information. In the normalized relational scheme, this can be easily done since the supplier name, address, etc. and the product name, product type, etc. are only stored once in the supplier and product relation, respectively. Furthermore, in this unnormalized relational scheme, it is also difficult to insert a new product for which there are no supplies yet, or a new supplier who does not supply anything yet. In the normalized relational scheme, this can be easily accomplished by adding new tuples to the product and supplier relation. Also, a deletion anomaly can occur. If we would delete a particular supplier from the supplies relation, then all corresponding product data may get lost as well, which is not desirable. In the normalized relational scheme, we just delete the corresponding tuple in the supplier relation, hereby not affecting any product tuples in the product relation. Finally, also an update anomaly can occur when we wish to update the supplier address in the supplies relation. This would imply multiple updates, with the risk of inconsistency. In the normalized relational scheme, we only need to do one update in the supplier table. It is clear that in order to have a good relational database scheme, all relations in the scheme should be normalized. Relational schemes that were generated from an EER scheme will automatically have this property if the translation rules were applied correctly. However, if the relational scheme was not derived from an EER scheme, a formal normalization mechanism can be applied to transform the relational scheme to a normalized form. The advantages are twofold. At the logical level, the users can clearly understand the meaning of the data and formulate correct queries. At the implementation level, the storage space is used efficiently and the risk of inconsistent updates is reduced. Before we start discussing a formal, step-by-step normalization procedure, let's review some informal normalization guidelines. First, it is important to design a relational scheme in such a way that it is easy to explain its meaning. Next, attribute types from multiple entity types should not be combined in a single relation so as to not cloud its interpretation. Also make sure that you mitigate the risk of insertion, delete, and update anomalies when designing your relational scheme. Finally, avoid excessive amount of null values in a relation. Here you can see an example to illustrate the latter. Suppose we have a relation supplier with attribute types supplier number, supplier name, and sub Twitter, which refers to the Twitter account of a supplier. Let's now assume that sub Twitter has many null values because not many suppliers have a Twitter account. Hence, keeping it in the supplier relation implies a waste of memory capacity. A better option might be to split up the supplier relation in two relations, supplier and supplier Twitter, whereby the latter includes supplier number as a foreign and primary key and sub Twitter. As we will discuss later, both relations can then be joined in case we want combined information from a supplier. Before we can start discussing various normalization steps, we need to introduce two important concepts, functional dependency and prime attribute type. A functional dependency, x to y, between two sets of attribute types x and y implies that a value of x uniquely determines the value of y. We also say that there is a functional dependency from x to y, or that y is functionally dependent on x. As an example, the employee name is functionally dependent upon the social security number. In other words, a social security number uniquely determines an employee name. The other way around does not necessarily apply, since multiple employees can share the same name. Hence, one employee name may correspond to multiple social security numbers. A project number uniquely determines a project name and a project location. Project name and project location are thus functionally dependent upon project number. The number of hours an employee worked on a project is functionally dependent upon both the social security number and the project number. Note that if X is a candidate key of R, this implies that Y is functionally dependent from X for any subset of attributes Y of R. A prime attribute type is an attribute type that is part of a candidate key. Normalization of a relational scheme is a process of analyzing the given relation schemes based on their functional dependencies and candidate keys to minimize redundancy and insert, deletion, and update anomalies. The normalization procedure entails various normal form tests which are typically sequentially evaluated. Unsatisfactory relation schemes that do not meet the normal form test are decomposed into smaller relation schemes. The first normal form states that every attribute type of a relation must be atomic and single-valued. Hence, no composite or multi-valued attribute types are allowed. We basically already discussed this before when we introduced the domain constraint. Multi-valued attribute types should be removed and put in a separate relation along with the primary key of the original relation as a foreign key. The primary key of the new relation is then the combination of the multi-valued attribute type and the primary key of the original relation. Composite attribute types need to be decomposed in their parts. You can see this illustrated here. Suppose we have a relation department. It has a department number, department location, and a foreign key referring to the social security number of the employee who manages the department. Assume now that a department can have multiple locations and multiple departments are possible at a given location. Hence, the relation is not in first normal form, since the location is a multi-valued attribute type. We can bring it in first normal form by removing the location from department and put it into a new relation, dep location, together with the number as a foreign key. The primary key of this new relation is then the combination of both, since the department can have multiple locations and multiple departments can share a location. Here you can see some example tuples. In the table above, you can see that department number 15 has two locations, New York and San Francisco. Department number 30 also has two locations, Chicago and Boston. The two tables below bring it in the first normal form. Let's give one more example. Assume we have a relation R1 with employee information such as social security number, e-name, d-number, d-name, and project, which is a composite attribute type consisting of p-number, p-name, and hours. Let's assume an employee can work on multiple projects and multiple employees can work on a project. Hence, we have a multi-valued composite attribute type project in our relation R1. In other words, both conditions of the first normal form are clearly violated. To bring it in first normal form, we create two relations, R11 and R12, where the latter includes the project attribute types together with social security number as a foreign key. Its primary key is then the combination of social security number and p-number, since an employee can work on multiple projects and multiple employees can work on a project. Before we can start discussing the second normal form, we need to introduce the concepts of full and partial functional dependency. More specifically, a functional dependency x to y is a full functional dependency if removal of any attribute type A from x means that the dependency does not hold anymore. For example, hours is fully functional dependent upon both social security number and p-number. Put differently, to know the number of hours an employee worked on a project, we need to know both the social security number of the employee and the project number. Likewise, project name is fully functional dependent upon project number. Functional dependency x to y is a partial dependency if some attribute A from x can be removed from x and the dependency still holds. As an example, p-name is partially functional dependent from social security number and p-number. It only depends upon p-number and not on social security number. A relation R is in second normal form if it satisfies first normal form, and every non-prime attribute type A in R is fully functional dependent on any key of R. Remember, a prime attribute type is an attribute type that is part of a candidate key. In case a relation is not in second normal form, we must decompose it and set up a new relation for each partial key together with its dependent attribute types. Also, it is important to keep a relation with the original primary key and any attribute types that are fully functional dependent on it. Let's illustrate this with an example. Say we have a relation R1 with attribute type social security number, p-name, hours. In other words, it contains both project information as well as information about which employee worked on what project for how many hours. The assumptions are as follows. An employee can work on multiple projects, multiple employees can work on a project, and a project has a unique name. The relation R1 is in first normal form since there are no multivalued or composite attribute types. However, it is not in second normal form. The primary key of the relation R1 is a combination of social security number and P number. The attribute type pname is not fully functional dependent on the primary key. More specifically, it only depends on P number. To the contrary, hours is fully functional dependent upon both social security number and P number. Hence, we need to remove the attribute type pname and put it in a new relation, R12, together with P number. The relation R11 can then be called works on, and the relation R12 can be referred to as department. Here you can see this illustrated with some example tuples. Note the redundancy in the original relation. The name Hadoop is repeated multiple times, which is not nice from a storage perspective. Also, if you would like to update it, then multiple changes need to take place. This is not the case for the two normalized relations at the bottom of the slide. To discuss the third normal form, we need to introduce the concept of transitive dependency. A functional dependency x to y in a relation R is a transitive dependency if there is a set of attribute types Z that is neither a candidate key nor a subset of any key of R, and both x to Z and Z to Y hold. A relation is in third normal form if it satisfies second normal form, and no non-prime attribute type of R is transitively dependent on the primary key. If this is not the case, we need to decompose the relation R and set up a relation that includes the non-key attribute types that functionally determine the other non-key attribute types. Let's work out an example to illustrate this. The relation R1 contains information about employees and departments. It includes the attribute types, social security number, e-name, d-number, d-name, and d-manager social security number. The social security number attribute type is the primary key of the relation. The assumptions are as follows. An employee works in one department. A department can have multiple employees, and a department has one manager. Given these assumptions, we have two transitive dependencies in R. D-name is transitively dependent from social security number via d-number. In other words, d-number is functionally dependent from social security number, and d-name is functionally dependent from d-number. Likewise, d-manager social security number is transitively functionally dependent from social security number via d-number. In other words, d-number is functionally dependent from social security number, and d-manager social security number is functionally dependent from d-number. D-number is not a candidate key or a subset of a key. Hence, the relation is not in third normal form. To bring it in third normal form, we remove the attribute types d-name and d-manager social security number and put it in a new relation R12 together with d-number as its primary key. The relation R11 can be called employee, and the relation R12 can be referred to as department. Here you can see some example tuples for both the unnormalized and normalized relations. Note, the redundancy in the unnormalized case, where the values marketing for D name and 210 for D manager's social security number are repeated multiple times. This is not the case for the normalized relations. We can now continue and discuss the Boyce-Codd normal form. Let's first introduce another concept. A functional dependency x to y is called trivial if y is a subset of x. An example of a trivial functional dependency is between social security number and name and social security number. A relation R is in Boyce-Codd normal form if and only if, for every one of its non-trivial functional dependencies, x to y, x is a superkey. That is, x is either a candidate key or a superset thereof. It can be shown that the Boyce-Codd normal form is stricter than the third normal form. Hence, every relation in Boyce-Codd normal form is also in third normal form. However, a relation in third normal form is not necessarily in Boyce-Codd normal form. Let's give an example. Suppose we have a relation R1 with attribute types, subnumber, subname, product number, and quantity. It models information about which supplier can supply what products in what quantities. The assumptions are as follows. A supplier can supply multiple products, a product can be supplied by multiple suppliers, and a supplier has a unique name. Hence, subnumber and product number are a superkey of the relation. Moreover, we have a non-trivial functional dependency between subnumber and subname. The relation is thus not in Boyce-Codd normal form. To bring it in Boyce-Codd normal form, we remove subname from R1 and put it in a new relation R12 together with subnumber as the primary key. The relation R11 can be called supplies, and the relation R12 can be referred to as supplier. We can conclude by discussing the fourth normal form. First, we introduce the concept of a multivalued dependency. There is a multivalued dependency from x to y if and only if each x value exactly determines a set of y values independently of the other attribute types. A relation is in fourth normal form if it is in Boyce-Codd normal form, and for every one of its non-trivial multivalued dependencies, x to y, x is a superkey. That is, x is either a candidate key or a superset thereof. Note that this normal form is often neglected in database modeling. Let's illustrate it with an example. Suppose we have a relation R1 including information about courses, instructors, and textbooks. The assumptions are as follows. A course can be taught by different instructors, and a course uses the same set of textbooks for each instructor. Hence, we have a multivalued dependency between course and textbook. In other words, each course exactly determines a set of textbooks independently of the instructor. To bring it in fourth normal form, we create two relations, R11 with course and textbook, and R12 with course and instructor. Here you can see some example tuples for the unnormalized and normalized relations. You can clearly spot the redundancy in the former case. Suppose a new textbook would be added to the course database management. In the unnormalized case, this would imply as many tuples as there are instructors teaching it, or 2 in our case. In the normalized case, only one tuple needs to be added. We hereby conclude the discussion of the relational model.